So today I'm going to discuss first the subject of group theory. This is a powerful mathematical framework and it helps in understanding what I described last time, the structure of languages, but it is useful in many other ways as well. And we'll use the ingredients in different forms at different types. I should also point out that there are books written on this subject. And I will describe what I need in less than a lecture. Okay, so it will be very concise and limited. If you really want to run the subject, you will have to take a full course on this and learn it in detail. Our purpose is limited, how it is useful for quantum computing, and I will sort of focus on that particular aspect. But the subject is quite straightforward and mathematically very easily defined, and it is rigorous as well. And the point is that despite its simplicity, it has very powerful consequences. And that is the reason it is widely used in lots of different contexts. So what is a group? So group is a combination of two things. One of them is a set of objects, and the other is a binary operations which act on these objects. So and this collection obeys specific rules. Okay? And those rules basically dictate what the group is. So I will write down the rules one by one. But there is one kind of implicit part of the description that mathematically these rules combining these objects which will be in general transformations are sufficient for describing whatever is going to come. But physics, there is a little bit more, which is kind of implicit. I should not use the word object. On which this transformation act. that is implicitly assumed to be there, and it is actually going to be the hardware when we describe the applications. What these transformations are going to do is they will define the state of the system. So to give a very elementary example is that I wear different clothes on different days. Okay. And those clothes are basically some definition of the state of the system. It implicates that it's the same person which is wearing the clothes. I don't have to write it down. So that is the hardware. So something which is there, it is fixed and it is changing its states. This change of the state are the transformations. That I was wearing this clothes yesterday, I'm wearing different clothes today, and that there is some change. And that is what gives the dynamics of the system in a certain way. And mathematically, that is enough, that you don't need to assume anything else. If you are given this set of transformations or changing, you will say that yes, the system was in this particular state and it's slowly changing its state this way, that way, etc., reaching somewhere else. Physically, it's implicit that there is a particular object which is fixed. It's a hardware which is changing state one by one in some particular manner. Okay? So this is always implicit. Mathematical textbooks actually will not bother to define this physics part at all. They will give a definition which only involves this transformation, and that is what I'm defining the rules to be. Okay? So what are the rules? One, that the system is closed under this binary operation. So if G I G J in G implies that all Gi whichever way you combine them, they also belong to the same group. This binary operation doesn't need commutativity. Okay, if you write Gj star Gi, it might produce something else. But it is assumed to be associative. Which means that when there are multiple operations, I can combine them in any particular order and it does not matter. So commutativity may not exist. So this is something very commonly which appears in mathematics, but of course you can construct mathematical formalisms which may not obey commutativity, may not obey even associativity, and they are not part of the groups. They will do something else. The third thing is there is something called a identity operation, which means do nothing. Whatever the property is, at the next step, it remains the same. That is very trivial to put in any dynamics. So there is a, well, I was using something else, so let me put a capital I. I combined with NEGI and for the identity, the order doesn't matter. And the last object in the list is inverse. That for if you combine the object with its inverse, you get identity. And here also the order doesn't matter. That's it. There is nothing more. And it's amazing that from such straightforward rules, how far you can go. I should also say that this particular symbol is generally interpreted as multiplication. Doesn't have to be, and we'll see lots of examples where it is not multiplication. But it's kind of convenient to use this because of all kinds of definitions of what you mean by inverse, which are all buried inside here in some sense or the other, and multiplication seems to be a straightforward description where identity just becomes multiplication by 1, and inverse is just the reciprocal. So this is the mathematical structure of the group, and now I can give examples with various kind of properties which follow from this particular list of rules. Before that, I can tell you a little bit of a story of the person responsible for creating this subject, and his name is Galois, a French um, individual with very interesting life story. The punchline is that he died when he was 20 years old. But what happened before that is actually also very interesting. Now people call him a mathematician, but he lived at the time of French Revolution. So he was very heavily involved in political activism. Well, all kind of demonstrations and riots and all those things were going on in France at that time, leading to what is now called the French Revolution. And he was involved in it from student days. And he was quite an active person, so the schools won't admit him. He was also jailed for his actions. And some of the work which went into all this was done while he was in the jail. No access to anything else, just working out whatever was in his head. And at some stage, he was finally released from the jail by a lot of his well-wishers arguing for him, saying that you are putting a wrong person in the prison, etc. And the notes of whatever he did in the jail were all kind of collected by him and put in some kind of a structure, because it wasn't going out. It wasn't going to get published in any place or anything like that. He was not in any such status. But on top of that, after coming out of the jail, he got involved in what the custom of those days was in a duel. So the story is that he had a girlfriend, and he was asked to defend her honor. Of course, the girlfriend had many suitors, and somehow that had to be settled. So in the duel, what people used to do is two persons will stand some distance apart and shoot at each other. And there was a rival. There were some people supporting both the sides, and they had a shootout. It was early in the morning. He got injured and he died. Not immediately, but neither the rival people nor his own people bothered to look after him after he was shot. They all disappeared. And somebody picked him up the next day. By that time, everything was gone beyond redemption, and he died. Now, he somehow had the idea that he is not going to survive the duel. So the night before that shootout, he was furiously writing down everything which he wanted to convey to the next generation, including some of this mathematics, and letters to his friends or whatever it is. And that survived. And the importance of all those documents was realized some years later by other mathematicians who continued this particular work, and the credit is given to him for formulating the whole subject. So that is the story of Galois. You can find it in many different places, but it just shows that there are many other things in life which influence a lot of things, what can happen and what cannot happen. So, okay, let me get back to the subject of the groups. The particular type of groups which turn out to be very important in many applications in physics, they are called symmetry groups. And they define invariance properties of a system. What do you mean by invariance? Is basically you apply some transformation and it looks the same. Like if you take a sphere, I rotate it, but it looks the same. So then you say that the sphere is rotationally symmetric. You can have all kinds of symmetries. You can have, say, a mirror image as a transformation, and then the symmetry is called parity. The reflection looks the same as the original part. You can have translation where you take an object and shift it, put it some other place, but the object looks the same except for its position. So these are all very simple transformation, but somehow they leave some things invariant. And this is extremely useful in physics for a powerful consequence that symmetry is always tied to a conservation law. Kind of intuitive that something doesn't change, which means something is constant. But what that object is can be explicitly mathematically connected, and in physics, conservation laws are extremely useful for lots of processes, and there is a corresponding symmetry transformation. Okay. So I will write down simple things. That there is a symmetry called translation, just moving the object from one place to another, and that is connected to conservation of momentum. That the system is having some momentum, you can move it, and then the new location, it will look the same. If you apply it to rotation, the corresponding object is angular momentum. The angular momentum will rotate the object, and if it is conserved, then the rotation will not do anything to the system. There is a time evolution which can also be a symmetry. The corresponding conserved quantity is energy. I am writing down the list which is intuitive with this state, but in physics you can actually provide a rigorous formulation of all these subject. Then the other thing which I already mentioned, that if you have a reflection as an operation, the corresponding conserved quantity is called parity. Reflection is like taking left to right and vice versa. So these are very important objects in physics. We use these conservation laws, and they are all tied to certain symmetries of the system, and for that reason the whole groups which are associated with this turn out to be very useful to study. Okay. And they are just called symmetry groups for not only well, simplicity, and well, you don't need any more fancy words. But physics, there are lots of examples of what are called internal symmetries, which are connected with internal degrees of freedom, like gauge theories have gauge symmetries, and what are called charges, which will have some kind of internal transformations of their various properties, which are used all over the place. We will not have reasons to use them, so I will not go into any more details about this. But these are the instances where applications with respect to computation will come in some form or the other. Okay. And that is something which I wanted to point out. Okay. The next object in the list, which is very useful, are what I call representations. So this structure was defined in terms of some set of objects and operations, but this is explicit realizations for those things in terms of linear algebras. So these are the properties were described in the, well, I should use the same words which I was writing over there. So because property got labeled somewhere else, so let me write it rules. So it is a map. So for every element, there is a corresponding matrix. And then This is mapped to the ordinary matrix product of linear algebra. Oh, I should put one label. To be able to do all these things, the matrices have to be square matrices. Otherwise, this product will not be defined, or rather it will go outside the space. So we know that square matrices, when you multiply them, you will get another square matrix. And if you can find such a map that for every element in the group, there is a matrix which does this job, then you have found a representation. What are the requirements of the rules? Well, there is an identity element which is needed, but we already know that the identity matrix exists, one of the square matrices, and it will do the job. Matrix multiplication is also guaranteed to be associative by its construction, so I don't have to worry about it. The inverse requires little more care, that the matrix inverse can be defined if the determinant is not 0. Okay. So these will all be matrices with non-zero determinant. Otherwise, the inverse cannot be defined, but that is fine. That is restrictions which can be put, and then one can ask, what are the possibilities? And there can be many representations for the same group, and even the I didn't say anything about the size of the square matrix, so whether it is 2 by 2 or 10 by 10, it could be anything. And that dimension of the matrix can vary. There will be many different representations, they will have different dimensions, etc. But all these matrices are useful, or other different representations can be useful in many different ways. And there are certain simple examples which can be constructed and which kind of gives you the type of variety which one can come across. So there is something called a trivial representation. It is all the elements are just mapped to the identity matrix. It's a many-to-one map, but there is no restriction on that. And then all the rules are trivially obeyed. Identity is its own inverse. And that is, well, that's why it's called trivial representation. There is nothing complicated in it, but it exists. Then there can be what I call matrices which are block diagonal. Block diagonal, well, I'll just draw a picture that there are definite blocks along the diagonal and the corresponding off diagonal stuff is 0. When you now ask what will happen with this matrix products, with this block diagonal matrices, is that the blocks don't mix. Whatever is the first block, you construct a product, it will take the first block of the second one and it will give you the first block of the third one, the result. So, if you have such a structure, the blocks don't mix, and then you can say that I might as well take one of the block as a representation. Perfectly okay. And so these things are called reducible that a more complicated thing can be broken down into simpler components. And most of the time then what people study are the so-called irreducible representations, which means that they cannot be broken down further by doing this kind of jugglery. Okay. So, we know that we can take two irreducible representations and put them next to each other to create a larger size reducible representation, but that is not going to tell us anything more. Okay. So this is certain properties, and these labels appear all over the place. That what are the so-called irreducible representation of some particular group? They are still not unique. There are many possibilities, and they are used in many applications. Okay. Now, one more concept which is useful is the so-called generators of a group. This follows from the constraint of this closure, that if I have certain elements, I combine them, I will still get some element of the group. So the question is, can I find a subset of the elements where all the other elements can be obtained by just applying these rules? And these are the subset of group elements and you are generally interested in this kind of generators to cut down the set of objects that you want to deal with. If you know how this smaller set works, then you know how the larger set will be constructed. Okay. And you are looking for many situations where this is not just a subset, but the smallest subset, which can produce all the rest. And yeah, now it is probably time to explicitly list examples to explain all these definitions which are buried in various forms. So, well, okay. There is, just like this trivial representation, there is a trivial group which doesn't have anything other than identity. We don't learn anything from it, but the smallest non-trivial group has lots of uses. And this is the object which in the previous lecture I denoted with the symbol Z2. So, what is the property? Well, I have two elements. And one of them is identity. I cannot do anything more. The second one has to be something different, not identity. But then I have the closure rule that if I take G, then combining G with itself should give me something back in the group. G multiplied by G cannot be equal to G because the inverse exists. So the only possibility is G multiplied by G can give me identity. There is no other choice. And so this object is its own inverse. That's the end of the story. There's nothing else you can do with a two-element group. And now you can ask what are the representations? And there aren't too many. There is a trivial representation which always exists, and the non-trivial one. And I'm sticking with this irreducible representation only, so I don't have to increase the list anymore. And this is a one-dimensional matrix. I can write it as number 1 and minus 1. Okay. This is under the rule of multiplication of matrices, so I multiply just the numbers for one-dimensional matrix. And there is nothing more you can construct. Actually, there is a theorem you can prove which tells you that if you know the number of elements in the group, you can figure out how many irreducible representations exist. It cannot be arbitrarily many. It's a constraint. And you can now denote this in a different manner, which is useful with a different operations. So instead of the multiplication, I take the operation as addition modulo 2, which is what this symbol uses. Then it is equivalent to this. It's just relabeling. But then 1 plus 1 is equal to 0 modulo 2. That's all I have to check.
Why did you write irreducible representation 1 comma minus 1? Why this is like irreducible representation?
Representation is a matrix. What is a one-dimensional matrix? It's a number. Find the matrix which obey the rules. Here. And you will have a unique solution. There is nothing else. Can you solve this equation for numbers?
This is for numbers.
Yeah, it's something which has to be obeyed by any representation of the group. I'm looking at one-dimensional matrix, which is a number. Solve the equation. X is equal to 1 over x for a number. If you can't do that, you have to learn back the high school algebra. Can you solve x equal to 1 over x?
Yes.
What are the answers?
1 minus 1.
Yeah, that's what it is. So this is a powerful group, and we use it to construct all of the binary arithmetic. There is nothing more needed for doing all the Boolean algebra and whatever follows. And it turns out that this object is much more powerful than just a group. And it has another name called a field. Again, goes back to Galois, who defined what is a field as well. And the field is again a set of objects, but which allows two operations, not one. One of them is the group property, but the other one is little bit different. And in this particular case, they are best understood as addition and multiplication. The addition part is actually a group. But the usual way we interpret multiplication, it is not a group. Because the identity element of addition, which is 0, doesn't have inverse in multiplication. So there is one peculiarity, one element is a little bit different, but you can still do many things by combining addition and multiplication. Keeping in mind that addition is a group, multiplication is group if you leave out 0. Then you can define inverse, but that one peculiar element prevents multiplication from being a group. But you can combine these two together and whatever comes out is called a field. And the natural construction which follows by combining these two together, which is generically used, is what is called a distributive law. Which is, you generally write, I will use I can do that by combining addition and multiplication, and that is possible in any field. Dot is a multiplication, plus is an addition in our usual arithmetic, and I can do this. And that gives it a whole lot more possibilities about what you can do using a field compared to what you can do using only a group. And we are quite accustomed to this number system anyway, so this is a very simple example where all these constructions can be done. And one can do all kind of more complicated things as well that, may be useful in different contexts. In particular, for several situations which we are familiar with, you can find the groups, but in general, for every number which I can specify that let the group have, say, 5 elements. How many groups I can construct of that type? And there are very strong restrictions. You just cannot do too many things. And so if you are given the number of elements in the group, you can do a lot of calculations without going into too many details. And I can give you some examples. Which are something called cyclic groups, which can be given as a list of objects where I just keep on taking higher and higher powers of one particular element, and at some stage I come back to identity. A simple illustration which is already here in some sense, this is addition modulo. Okay. I can illustrate something more explicitly here. So it has only one generator, which is G. If I know G, I can construct all the rest. This addition modulo and like a translation group. I have 0 as the identity element for translation. I have 1, and then I keep on translating 1, 2, 3, 4 as far as I want to go, and that will generate all the elements, all integers. If you want to cut it off at some point, you can do modulo n. If you want to let it go all the way, you can generate the whole line, no problem. So for this, the inverse is, instead of addition, subtraction. You can go from 0 to 1 by addition, 1 to 0 by subtraction. But the point is that you are using only one element G. If G is addition by 1, G inverse is subtraction by 1. And this is a kind of a situation which again, something that can be proved, that if the number is prime, then this is the only group you can construct. It's a theorem. If there are factors of n, you can do many other things, but if it is prime, there is no other choice. This is the only group which can be used, and it has applications for that reason in number theory. And these groups, whatever I have listed here, they are all commutative. But I can go beyond that. The addition or translation is by construction commutative. We don't know anything else, but we have other possibilities that these are matrices. And matrices for dimension larger than 1 don't have to necessarily commute. So that also is kind of buried inside here for various constructions which I did. If I have a group which is commutative, it allows only one-dimensional irreducible representation. There is no choice. So the higher matrices you try to construct, they will all break up into this block diagonal form because they have to commute. If you take a bigger matrix with non-trivial off-diagonal entries, they don't necessarily commute, and then you won't have the possibilities. But the interesting possibility where there are non-trivial objects, I have to look for a transformation which doesn't commute, And the well-known example is rotation. That uh, time is up. Okay, I can finish. We know for the fact that the rotational transformations in dimension bigger than 3, they don't necessarily commute, and they have irreps of dimensions which are bigger. So they are not really matrices. If you have a commutative group, they are numbers. But even with numbers, you can do lots of non-trivial things. And for example, if you want to find representations of these things, you will need numbers whose nth power is equal to 1. You can't solve it using real numbers. You have to go it in the complex plane. But complex planes, once you accept it, they are nth root of unity going around a circle. So the representations can turn complex, that is fine. But here you can have representations with dimension bigger than 1 as well when you start dealing with rotations, and they are very common in describing the symmetries of crystals, where you have some discrete set of points and you rotate in 3 dimension, you will kind of come back after a certain number of rotations to the original configuration. So if it's a square or a cubic crystal, the simplest called generator can be rotation by 90 degrees. You do it 4 times, you will come back to the starting point. So that will define a subset which has this property running 4 times. But you can do it in multiple dimensions. They don't necessarily commute, and you can generate a more complicated structure from there. And the group which is going to be particularly useful to us is the SU2, which I will discuss in more detail next time. But it is exactly this group of rotations in 3 dimensions. And we will heavily use this particular group in constructing our quantum system. Okay. I will discuss that in the next class. And you can keep on adding to this list. It's a vast subject, but I think this is enough for the time being. And yeah, I can point out one thing here, which I said, that this irreps can be complex. And for that reason, the matrices which have inverse of a certain type, which is says and they so there is a particular set of matrices which we'll use heavily. They are unitary matrices, and in particular, they also have determinant equal to 1. These are all the details which will be needed to build up the structure for SU2, but they are not the most general thing. There is a little bit of specialization in going from an arbitrary group representation to these cases. And I will stop at this stage here.